In this video, we are going to do an example where we have a triple integral where I need to sketch the region of integration and then convert it to spherical coordinates. So let's get this started together. And I noticed that the innermost integral has a dz. So these limits of integration are in terms of z. So this is z equals this square root is z equals that square root. And I'm going to want to think about what do these surfaces look like. And if I keep going this way, next up I have dx. So this will be x equals 0, and x equals this next square root. Finally, we got dy, so this will be y equals 0, and y equals 3. So at this point, I want to give you a chance to pause the video to try this. So pause the video for about 5 minutes, at least 5 minutes, to try this on your own. So pause it in 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. Let us talk about it now. So I am going to go ahead and first notice that if I think about this equation up top, well, if I were to square both sides and rearrange it, I'll get x squared plus y squared plus z squared equals 18. And that's the equation of a sphere. But if I go backwards and I isolate both sides, isolate the z and I square root, I would get a plus or minus in front of the square root. So the fact that there's no plus or minus, it means that this z value is going to be non-negative. So it can't be the whole sphere. It's only the part of it where z is non-negative. That is the top half. So that is called a hemisphere, half of a sphere. Okay, so I'm going to go ahead and start to draw a picture. So I'm going to draw my axes. I'll draw my z-axis, my x-axis, x-axis, my y-axis. And then I'm actually going to draw two sets of axes because I'll draw an initial sketch and then I'll clean it up as I go. So the top half of the sphere. Okay, so I'll do my best to draw this top half. And then I'll draw this circular base. The circular base, do my best to make it look 3D. Circular base. I got something like this, that top half. Okay, so then what about this bottom limit of integration? Well, z equals the square root of x squared plus y squared. That is a cone. That is a cone where its vertex is at the origin. And then I draw upwards. Draw upwards. We've seen that a bunch, I think, in multivariable calculus. Okay, so I got this upward facing cone. I'll draw one of these circular cross sections to make it look a bit more 3D. So I got this cone that's slicing through this hemisphere. So in my new axes, I'm going to try to draw a cleaner picture of that. So let me also draw the negative y-axis a little bit. I'll draw it in both of these pictures. Okay, and so for this region, it has the cone at like the bottom. The cone forms sort of the bottom of this region. And then where the cone and the sphere intersect, that's this circular cross section. So I'll draw that circular cross section. And then above that circular cross section, well, then I'm on the hemisphere. The cap is made of, let's go to draw mode. The cap is made of the sphere. So I get this ice cream cone shape. Okay, so what I still need to deal with these limits of integration for x and y, because those will tell me, well, is it the whole ice cream cone shape or is it just part of it? So I now think about the shadow for those two remaining limits of integration. The shadow on, because these are x and y, the xy plane. Shadow on the xy plane. So I'll do this in this initial sketch first. So x starts at x equals 0. The graph of x equals 0, that's just on the y-axis. And then x equals the square root of 9 minus y squared. That's a semicircle. That is a semicircle. Right, because if I square both sides and rearrange it, I get x squared plus y squared equals 9. That's a full circle. But then isolating the x by square rooting, I don't have that plus or minus, so it's just going to be half of the circle. In the same way that this was the hemisphere, this is half of the circle, where x, these outputs have to be non-negative. That tells me it's the right half. It is the right half of that circle. Okay, the right half of that circle, where The radius here is 3. The radius is 3. And then it tells me that then y goes from 0 to 9. So the smallest value of y should be 0. The biggest value should be at 3. So the region we're talking about, I'll call it R, is this quarter circle actually. So I'm going to do my best to draw that in this cleaned up picture. So this quarter circle base should be directly below kind of how far the cone extends up top. So if I think about the circle here, and I draw straight to the right, and then I drop that straight down, that'll form this point on my quarter circle. And from that center, if I draw a line parallel to the x-axis to that edge, and then I draw a line straight down, that'll be this point on my quarter circle. So now I can connect those, and I get that quarter circle base. I'll color it in. I'll call it R. Okay, nice. So I'm getting that base region. And then I'm slicing out a wedge of this ice cream cone. So I'll connect this to that point up top on the z-axis, and then I'll connect that to this point here, and I'm getting essentially a quarter of the ice cream cone. I'll also connect this point to the origin. So a quarter of the ice cream cone. I'm cutting that out. Okay, so I've sketched the region. We're now ready to convert this thing to spherical. It asked me to convert it to spherical coordinates. Okay, so when I do that, I'm going to get a new triple integral. So new triple integral, I'll space these out. Where first I got to take my function and convert it to spherical. So x squared plus y squared plus z squared. I will highlight that. In spherical, remember that just becomes rho squared. Then I do my absolute value of my Jacobian, which is rho squared times sine of phi for spherical coordinates. Then my new variables, d rho, d phi, d theta. Okay, and now my limits of integration. So the innermost one is rho. So where does rho start? Where does rho end? So to answer that, I draw an arrow from the origin radially outwards. And I think about when does it enter the region? It enters it right away. That's when rho equals 0. When does it exit it? So it exits when I hit the surface of this hemisphere. And the equation on that surface is for sphere, well, it's just rho equals whatever the radius is. And the radius is square root of 18. So that's when I exit. So that's that upper limit for rho. Next up, I need phi. So what does phi go from? So I draw an arrow straight up on the positive z-axis. And right now we've already entered the region. And that's when phi equals 0. That is when phi equals 0. And then I keep going out away from that until I exit the region, which happens here. And on this cone, that forms a 45-degree angle, which in radians, that is pi over 4. That is pi over 4. And then finally, I need my values for theta. So for theta, and I can figure these out based on this base shadow. For that base shadow, theta equals 0. That's here. That's this direction. That's where I'm starting. I've already entered the region. And then if I keep going up until this point, that's when theta equals pi over 2, or 90 degrees. So theta equals 0 up until pi over 2. And there we have it. It just wanted me to convert it to spherical coordinates. It didn't ask me to evaluate it. And at this point, we have done that. So in terms of our goals for this section, we finished our last goal. We've learned how to evaluate triple integrals using spherical coordinates. And maybe more importantly, we've discussed how to recognize when that is beneficial to convert to spherical coordinates. It's often when we have shapes like spheres and cones, because their equations are just much simpler in spherical coordinates.